well as the Suvat equations, another formula that comes up repeatedly in mechanics is this idea of F equals ma. That is to say, force, or specifically resultant force, is equal to mass times acceleration, where the force is going to be measured in newtons, the mass is going to be in kilograms, and the acceleration is going to be in meters per second squared. Now, what we mean by resultant force is to say that if we just had an object, say a block here, which say was 5 kilograms, and it was going to have a 10 Newton force pulling it to the right, however then it would have a 2 Newton force pulling it to the left. Well, the resultant of this, the overall, would be 8 newtons to the right, because they're going 10 to the right, then minus 2 from it back to the left, you've gone 8 to the right overall. From this, using this formula, therefore, we could work out what the acceleration of that object is. We could say that the resultant force, 8, is equal to the mass of 5 times the acceleration. Therefore, the acceleration is going to be 8 over 5, or 1.6 if you prefer as a decimal. Alternatively, we could start knowing the acceleration, but we don't know one of the forces. Let's say this time an object is moving vertically. We'll give this one a mass of 6 kilograms. Now, if we're moving vertically, and we'll say freely under gravity, if you want just a refresher on the parameters of moving under gravity, there is the Suvat under gravity video that you can look at as well. But in general, if we're moving freely under gravity, then the downward force is going to be the weight. The weight we get from the mass times gravity, so that would be 6 times the 9.8. Let's say we now don't know this upward force, this up thrust here. Yet we know that the acceleration is going to be, let's say, 2.5 in the upward direction. Okay? Well, because we are accelerating upwards, we're going to presume that this whole object is travelling upwards, therefore. So the thrust is going to be our forward force. You would then minus the resistive force, which in this case will be this here, the 6 times the 9.8, and that will equal the mass of 6 times the acceleration of 2.5. Well, at this stage, we could then add the 6 times 9.8 over, which will give us the equivalent of 15 add, and that other bracket comes to 58.8. Therefore, your tension is going to equal 73.8 newtons going upwards. Now, this is just for a single isolated object, though, and you may have scenarios involving these. You just have to work out if it's in equilibrium, then it is stationary, that the forces in one direction will equal the force in the other direction. Equilibrium will be dealt with more thoroughly in later videos. But we could also have connected particles, and we're going to refer to them as particles because that will help us just imagine that their mass is concentrated in one area. That's only one kind of assumption that we can make, though. So we can say that if we assume that these things are particles, then that means their mass acts at one point. We can also, when we're looking at these connected particles, make other assumptions about how they are connected or the surfaces they are touching. If the thing that connects them, so a string or a tether or a tow bar or something like that, if that is described as being light, that means that you can ignore its mass. That its mass is negligible, it doesn't make a difference to the scenario. If it is inextensible, then that means that the acceleration is equal throughout. So if you have the acceleration of one part of the system, it's the same as the acceleration of another part of the system. It's the same as the acceleration of the whole. And you can also say maybe the surface that they're traveling along is smooth. That would mean that there would be no friction. And it would also mean that in the case of pulleys, the tension is equal throughout. But pulleys are something that will be given a video in their own right later. For now then, if we're just appreciating what these words can mean, just these mathematical caveats that we can have just to make our lives a little bit easier when doing these equations, let's just look at how we can model connected particles then. In the scenario here on the right, we have a car of 1,400 kilograms and a trailer of 700 kilograms connected by a light inextensible tow rope have a constant resistances of 630 newtons and 280 newtons respectively. So that means that these numbers apply in the order that the names were said. So the car is 630 and the trailer is 280. A driving force from the car is 2,380 newtons. Find the acceleration of the car, the tension in the tow rope, and state how you would use the assumption of them being particles. In these kind of questions, I always suggest that you would draw out some kind of sketch to represent the model, just because it helps you visualize things and make sure that you're labeling everything that can be labeled, considering every number that could be considered. With any mechanics question, if the scenario changes later on, I will then also say redraw the diagram from scratch, just to make sure that when you're going through your working, you're not incorrectly continuing to use certain numbers that aren't meant to be present anymore. In this case, because it's a car and trailer, you don't have to draw them anyway accurately with imagining they're particles anyway. So let's just give a box for the car and a slightly smaller box for the trailer, and they are connected by a horizontal tow rope. So the car has the mass of 1,400 kilograms, the trailer is the 700 kilograms. There will be a tension in the tow rope. Tension and thrust are the two kinds of forces we can get in any kind of connecting line. They're constantly acting in both directions in every single place. We're just visualizing it, that in this case the tow rope will be pulling back on the car as the trailer weighs it down, whereas the car will be pulling forwards with the tension on the trailer, hence why the trailer moves forwards. If the car was to be slowing down, the directions of these would switch and it would become thrust, because as the car is slowing down, the trailer would now be pushing into the car as it still tries to speed on, and then the car will be pushing back on the trailer. In this case, though, the key is that tension comes back on the car and tension comes forward on the trailer. If it was the other way around, the trailer wouldn't have a forward force, therefore it wouldn't be moving forwards with the car. We also have some other forces we can label on. You've got your resistive forces, so maybe because it's with the road, you can put it at the bottom, but you don't have to. So 630 newtons for the car and 280 newtons for the trailer. And then the car also has a driving force of 2,380. Now that we've labelled all the forces and we have the masses, we can start to construct an F equals ma expression. Right now we don't know what the tension is, so if we were to just focus on the car or just focus on the trailer, we would have an unknown. So what we have to do instead is consider the model as a whole, because if we were to then list all of the forward forces and then take away all of the reverse forces, the resistive forces, the plus t minus t, because in opposite directions, would cancel with each other, removing the unknown from our expression. We would therefore just be left with this forward force of 2,380 minus the resistance of 630 and 280. And this will leave us with mass times acceleration, so the combined mass of the whole thing is 2,100, and we can just say that that is times by a for now, for the acceleration. Here we can therefore just work out what the left-hand side is, type it into your calculator, and then divide by the 2,100 to get you A on its own as 0.7 meters per second squared. Now that we know that this is the acceleration of the system as a whole, because the string was inextensible. We know the acceleration is equal throughout, so the acceleration of an individual, either the car or the trailer, will also be 0.7. We can now focus on one of those individuals, because doing so will now bring tension back into the equation. If we continued looking at the whole system, they would continue to be cancelling with each other. It doesn't really matter which one you focus on, it will get you the same answer regardless. I'll just suggest look at the trailer, just because there's one fewer forces, but it doesn't really matter. Again, we're going to construct an F equals ma, so we need a forward force, take away any resistive force. In this case, the forward force on the trailer is the tension, and then take away that resistance of 280. That equals the mass of 700 times the acceleration that we now know to be 0.7. So if we times the 700 by the 0.7 and then add the 280 over, you end up with tension being 770 newtons. If we had just double checked with the other one, so okay, that forward force is 2,380, and then with minus both the tension and the 630, that would equal the 1,400 times 0.7. So you do 1,400 times by 0.7, and t onto the right hand side, and we'll move, well, this is essentially 980 onto the left as a negative now. So you have t is the 2,380 minus the 980 minus the 630, which, yeah, leaves you again with 770 newtons, just to confirm. Now after that, just state how you would use the assumption of them being particles. Well, again, that assumption is telling us that their mass is acting at a single point respectively. This means we don't have to worry about the distribution of mass of weight when we're doing the calculations. Now it's at this stage that we might have what I mentioned before of the scenario changing, at which point we may have to change our model in turn. So if we were just to have that when the car and trailer are moving at 14 meters per second, the tow bar brakes. The driving and resistive forces remain unchanged. Find the distance the car travels in the first 4 seconds afterwards. Well, because the tow bar is broken, our model will have changed, as I say. So we're just going to have the car on its own. The trailer is no longer connected. It's not part of the system anymore. So that car still has a mass of 1,400 kilograms. And it's also confirming here we still have that driving force of 2,380 newtons, as well as the resistance on the car, which was the 630 newtons. We, however, do not have the tension or the thrust in the tow bar anymore. This means that the resultant force is going to be different. This means that the acceleration is different, and because of that we have to work it out from scratch. So once again, resultant force, we'll have our 2,380 minus the 630. That will give us 1,400A. So if you were to divide the left-hand side by the 1,400, that leaves you with the acceleration now being 1.25 meters per second squared, as opposed to the 0.7 from before. With this acceleration, given that we're now looking at distance, we can actually now construct a suvat. If we're not familiar with the suvat equations or want a refresher on them, you can go through the video on that explicitly. But here, if we just first of all write out our 5 variables, so the s for displacement, u for initial velocity, v for final velocity, a for acceleration, and t for time, we're after the displacement. We know that the initial velocity in this case is 14 because this model changed, it appeared this way when they were moving at 14, so that's our initial here. We don't know the final velocity. The acceleration we just got was 1.25, and the time we're saying after 4 seconds. So we don't need v here. You've got s, u, a, and t. We'll use s equals ut plus a half a t squared. So here you essentially have, so the 14 times by the 4, add to half times 1.25 times 4 squared. Putting that all in your calculator gets you a distance travelled of 66 meters. Okay, If we're happy with that, and we can see how, if we can draw out a model based on a description in the paragraphs, with some objects, with some masses, with some forward forces and some resistive forces, using these annotations, we can construct an F equals ma to find out any missing variables, determine whether we look at the whole model or one individual part of the model, and then potentially, if the model changes, redo the model, and then that may allow us to get something to do, in this case, a SUVAT. If we're happy with all of that, let's just see how you would get along with an example of your own. You are given this diagram here, where you have particle P connected by a light horizontal rod to particle Q, and particle Q then has a 30 Newton force applying on it in a rightwards direction. So we're told P and Q, first of all, have masses of 4 and 6 kilograms respectively. They start from rest, which, if we remember, means that their velocity is 0, and when we think about SUVAT questions. Their resistive forces are 2 newtons and 4 newtons respectively. The force is applied for 5 seconds. Okay, now with this information, find the acceleration, the speed at 5 seconds, and the tension in the bar. Additionally, once we have this, we will say, so after the 5 seconds, force is removed and they decelerate to rest again. With that in mind, find the distance travelled by P while it's decelerating, as well as the thrust in the rod, again while it is decelerating. Consider all the information that we have here. What might apply to what, when, how might things change? Think back maybe to what we did with the previous example, and overall just pause the video, try to have a go for yourself, and then press play again when you're ready to compare. Alright, so first of all, if we're looking for the acceleration, then we need to make sure that all of our forces are noted on the diagram. So P is having a resistive force of the 2 newtons, and Q is having a resistive force of the 4 newtons. There is also a tension to begin with in the rod, but if we consider the model as a whole, that cancels out with itself, leaving us with just a forward force of 30 minus the resistive forces of the 2 and the 4, and that's going to give us, so the combined mass is going to be 10 times your acceleration. Well, the 30, what is essentially minus 6, is going to be 24, so 24 divided by 10 leaves A being 2.4 meters per second squared. That's your acceleration. As for the speed after 5 seconds, well, we know they start from rest, so your U is 0. We're after the V, A is that 2.4, and T is going to be the 5 seconds. So V equals U plus AT, so it equals 0 plus 2.4 times by 5. That's going to give you a speed of 12 meters per second. And from that, just find what the tension is. Again, at this stage, we'll just focus in on one of them or the other. I'll focus on P. So for P, the forward force is just the tension, minus the only resistive now of 2, gives you the mass of P was 4, and that's times by the acceleration of the 2.4 here. So your tension is going to say 4 times your 2.4 here is going to be 9.6. Add the 2, gives you a tension of 11.6 newtons. It's at this stage though that the model gets changed, so we're going to have to change what's up here, remove that forward force. The tensions are now going to become thrusts in the opposite directions. And if we also just clear a bit of this space here because we no longer need it, because again the situation has changed, the acceleration has changed, and so all of these other numbers here aren't relevant anymore. For working out the distance travelled by p while decelerating, even though it's not telling us to work out acceleration again, we are going to have to under this new thing here. So once again, by considering the model as a whole, the tensions, or now the thrusts, are going to cancel, leaving us with only resistive forces, so only the -2 and only the -4, so -6 overall, now being 10a, therefore a is going to be minus 0.6 meters per second squared. From that, we can now get another suvat. So we're after the distance travelled. The u here is going to be the speed after 5 seconds, which was our 12 from before. The v, because we know it's decelerating to rest when it's going to end at 0. The a is the minus 0.6, and we don't know how long it takes to get to rest, so we don't have a t. This is fine though, we have 4 variables. We can say that v squared equals u squared plus 2as, so 0 equals 144 plus 2 times minus 0.6 times by your s. So if you were to add this onto the side here, you end up with 1.2s equals 144, so s on its own is going to be 120 meters. So for the thrust, just like with the tension, we'll just focus on one of them. Let's say that we'll focus on P again. So you've got your -2 minus your T, that's going to equal the mass of 4 times your acceleration of minus 0.6. So we want to add the T over here to make it positive. And here, because this, what is essentially 2.4, is already a negative, when we move it over, it becomes positive. So the -2 adds to 2.4, leaves us with a tension of 0.4 newtons. Okay? If we're good with that, let's then just wrap up with one other kind of question here. Now, this is different to what we were just having, because these aren't two separate particles that are then connected by a rod. This is an object inside of another object. And so, in fact, this actually comes from slightly ahead in the chapter than the connected particles. However, because I personally feel it's slightly less common in practice, and because it may be slightly less intuitive, I just want to address it as well here and now at the end. So, a vertical rope AB has its end B attached to the top of a scale pan. And the scale pan has a mass of 0.5 kilograms and carries a brick of mass 1.5 kilograms as shown in the diagram. The scale pan is raised vertically upwards with a constant acceleration of 0.5 meters per second squared using that rope AB. The rope is modelled as a light inextensible string. So from this, we need to find the tension in the rope and then the magnitude of the force exerted on the scale pan by the brick. So because we are dealing with a situation where a constant acceleration is being produced by forces acting in opposite directions on a moving object, we are indeed going to once again be producing F equals ma equations. Before we do construct these though, it's probably best that we get a diagram that is fully annotated for this. You can use the one that the question has given you, or you may just wish to draw out your own on a slightly bigger scale, just so that you can get more room to annotate, and it also gets you to draw everything for yourself. Make sure that you're acknowledging every part of the diagram. So here, for instance, we know that there's going to be an upward tension in this string, this rope, because ultimately the system is moving upwards with an acceleration of 0.5 We also know that the scale pan has a mass of 0.5, so this means that it's going to have a weight going downwards. All objects in any situations like this are going to have a weight, which, if it wasn't clear already, is got by mass times gravity. So in this case, that would be 0.5 times 9.8. More than this though, there's also some forces relating to the brick. The brick also has a weight coming down. That's going to be 1.5 times the 9.8, again, so mass times your gravity. As well as this though, there's still a couple of others. You also have the reaction forces. Now, whenever two objects are going to be touching, they're going to generate a reaction force with each other. When you walk, you press your foot down into the ground, but the reason why then you move forwards is the ground pushes back up on you. The reason why this brick isn't just dropping through the bottom of the pan is because the pan is pushing back up on the brick with its own reaction force. To be clear, this is not a force that is affecting the pan. The force is only affecting the brick. Similarly, the brick is going to be pushing down on the pan with an equal reactive force, just in the opposite direction, because again, they're touching, they're going to try to be pushing away from each other. So these reactions are opposite, they're the same magnitude, but they're in opposite directions. The upward one only affects the brick, the downward one only affects the pan. With that in mind, we can now start creating those expressions. And we have, so far, two unknowns. We know neither T nor R. So we're going to do what we did before with like the connected bodies, where we didn't know the tension in the tow rope, in that we're going to consider the whole model to begin with. If we consider the whole thing, because these R's are the same number, just in opposite directions, they will cancel with each other. So we don't have to worry about them. This just leaves the forward force being T, with the resistive forces then being the combination of the two weights, so 0.5 times 9.8 and the 1.5 times 9.8, which, if you like, you can just think of as the same as T minus 2 times 9.8, the 0.5 and the 1.5 together. This equals the mass times the acceleration. Again, we're going to be considering the entire mass because we're looking at the whole model. So the 1.5 to add 0.5 gives us 2, and the acceleration from before is 0.5. So if we just want to get t on its own, that will equal 2 times 0.5, which is going to be 1, and then you'll be adding over what is 19.6, giving us a tension overall of 20.6 newtons. Now then, for the magnitude of the force exerted on the pan by the brick, so that's this downward force here, what we can do is we can now just look at the pan. So in this case, again, our forward force is going to be tension, which you actually now know to be the 20.6, and then that's going to be minus 4.9 is the 0.5 times the 9.8, and then also minus that R that we're after, and that's going to equal the mass now just of 0.5 times the acceleration also of 0.5. Now we're looking to work out what R is, so we're going to want it to be a positive, so you can add it over to the right hand side, and then we'll minus what is 0.25 essentially, so you've got 20.6 minus 4.9 minus 0.25, that gets you that reaction force as being 15.45 newtons. Now, because these reactive forces aren't equal to each other, you would have been just as able to work out what the reaction force on the brick would have been. And then again, you just say that it's the same magnitude. If we just want to check that though, so because the brick is moving upwards, this R is now the upward force, and you're going to minus this resistance here of 14.7, so the 1.5 times 9.8, and that will give you the mass times acceleration of 1.5 times 0.5. So you end up with R equals 0.75 add the 14.7, which again gets you 15.45 newtons. The one advantage maybe of doing it around the brick is that it doesn't rely on you having got the tension beforehand, so you could do part B even if you hadn't got part A. However, if it helps you in any way just to understand which forces are affecting which, because we're specifically looking at the force of the brick on the pan, you may also want to do the left-hand version for that advantage, that you are definitely looking in the right direction and you can be confident in that.